starts working on all 4 assignments on Wednesday, look how it goes. That's not the plan. The plan is that everyone should have already finished assignment 0. You didn't have to, right? There's a flexibility on the deadline, but if you're like, oh, I'm going to submit the beat for the next week because my semester only gets easier the longer I wait. If that's true for you, great. It's probably not true for most people. So get on that right away. Anything else I want to say about all of this? You have to go to the right side. If you've accepted an invite, you've gone to the github.com/notifications or organization page, and it's still not there, you look for your spam emails, then waited an hour, send me an email or a message on, I think I'll probably search the Piazza for this to help get it produced. You can find the links to the course website. Not all of this. It's building this Lola. So for example, right, but the Java program running on that virtual machine is just an application. So that's not to say that these languages are better, it's just they allow us to control this whole thing. So higher level languages are generally what we're going to need for most things. So if you don't need high level of performance, you're probably not worrying about C. You want to choose a language that fits the programming goals. Each one has different trade-offs. Where's the language chosen for us? Okay, so we are stuck with C. And we're going to be doing things like worrying about memory access. Okay, so I told you C or C++ and memory. What are some of the words that come to your mind and maybe haunt your dreams? Yeah. Pointers, yes. Alec, yes. What else? What else haunts your dreams with C and C++ and memory? Yeah. Free. Alec, free. That's good. Yeah. What else? Leaks. Memory leaks. Yes, that's a big one. What else we got? What else could possibly go wrong? Yeah. Segfaults. Oh yeah, we'll definitely get those. Yeah. See? Oh, boundary errors. Yeah, like out of bounds. Like you got the 10th element in a 10 element array. Clearly, it's beyond the end. Yes. What else we got? Yes. Oh, dangling pointers. Yes. All of these things will haunt our dreams. It's okay. We've got tools that will help us sleep well. I guess maybe actually sleep. So we'll look at some of those tools and see how we can, get out of this kind of memory hell. But you're gonna have to think about that. So get your brain working on thinking about memory access and that. We're gonna look at the stack. We've got the hardware, OS, and the application. We're gonna look at it bottom up. Let's start with the hardware. So what do we need to know about hardware? First off, there are 2 fundamental components in computing. First, the computation. Computation is handled by our CPU in general. There's a lot of parts to that. Now it might also be handled by your graphics unit and so on and so forth. But as a fundamental level, we've got computation. We need to be able to do some operations. Do all the operations we want, whatever those happen to be. And not only computation, we need data to work with. We need to know if we're playing a game, we need the data of a level, or we need the texture to render, or we need to know the size of the projectile we're shooting. All those things with data, and then the computation combined. Now this is interesting because these 2 things are handled by the computer. They're kind of fundamentally in the same spot, but how they get processed is different. So data is handled by your main memory, also called RAM, which is, what is RAM? You know RAM? What's it stand for? Random access memory, which is kind of a funny name. I don't want my memory to be randomly accessed. You have a random access bank account? Doesn't make sense. It's called random access because you can access any part of it at the same speed. You can randomly pick a point, you can access the same speed at the same speed. So your random access memory or your storage and your hard drive. So let's look at the not particularly complicated command here. I'm going to take 3 variables. I got A plus B goes into C. The equals greater than means I'm going to put the answer in C. This isn't C notation. It's just sort of showing what's happening. So in this, what part of this is computation? Scissor? The addition, yes, also. The assignment, yeah, so we added the 2 numbers together, and then we put them somewhere. That's the operation. The data is whatever was in A and B. It loaded a value from A, and it loaded a value from B, wherever they happen to be stored in the computer. So the data and computation. Inside the computer, the foundation of everything is your motherboard. It kind of holds, it's the glue that holds everything together. Modern computers are what's called von Neumann architecture. It is the current winning design. It's not like AMD versus ARM, they're all von Neumann architecture. In the von Neumann architecture, we've got the data from the memory, fetch data from memory to provide it to the CPU. Sort of this, we take data in, we feed it to the CPU. Also, another fundamental property of this is that the instructions are stored in the same place as data, which is really cool. Your hard drive stores computation things, like instructions, as well as data. And that's actually incredibly powerful, because you want to change your program, you want to update Windows, that's just data on a hard drive. So other components we've got the CPU, so inside of here, this flat spot is the processor socket. The processor itself is about the size of a business card, kind of. And it sits in there with a whole bunch of little pins on the bottom. It slides into that socket. In the background behind it, I've got 2 here, DRAM, or 4 actually, RAM sockets. A RAM chip is about this long. It slides in. You put 1, 2, 3, or 4 in, or more maybe. And on the right-hand side of that, what's called PCI bus. This is where you put in extra cards. For example, your graphics card would be a common thing you put into here now. If you're trying to access custom hardware or sound card, you might also slide it into there. Less common now than it used to be. It used to be you'd get a lot of things like your sound card, modem, Ethernet card, serial card, and you'd have 5, 6, 8, 10, maybe not 10, 6 things plugged into here. Most of those have now become things that are just on the motherboard. So here's the audio and so forth. So the motherboard kind of ties it all together, gives us the actual low-level hardware components. One interesting thing about the computing is just how fast it is. So if you think about a lot of things in life, how fast people run, for example. Anyone here an Olympic level sprinter? No. Okay. Anyone here think they could run faster than the fastest human 100 years ago? Maybe that one person's like that. Not me. Anyone think here that the computing power that's on your wrist is faster than what the world had 100 years ago? Yeah, right. You had like an abacus or a slide rule or this kind of thing, right? What landed on the moon, my watch is more powerful than what landed on the moon to start with. So what's going on with that? So what we've got is advances in engineering. Given a certain area of a chip, how many transistors can you put on that chip? Well, to begin with, you couldn't put many. And then they got better at making them. You could put twice as much. And you could put twice as much again. And we kept getting more and more transistors in the same chip size. So that's this data here, thousands of transistors, that's the orange. It's a logarithmic scale vertically, linear scale horizontally. So we are, of course, now about here. But anyway, look at the trend here. This trend, you kind of blur your eyes a little. It's kind of a straight line on a logarithmic scale, which means it's exponential growth. Exponential growth in the number of transistors that you can put on a chip. Cool. And for the longest time, the blue line just below it was single-threaded performance. You got one processor, one process running one thing at a time. How fast could you do it? And in the beginning, we talked about kilohertz, but we very quickly got into megahertz. What's the slowest computer, desktop computer, you've ever run? Slowest, in terms of processing speed. Yeah. Say it's right? The Commodore 64, do you know the clock speed on that? No idea what that was. Okay, my first one was a 286, which ran at a blistering 12 megahertz. It was too fast for a lot of the programs. So you had a program actually that would slow it down to the XT 6 megahertz. So that's, well, you can find where that is on the graph. That's pretty slow. Now your watch probably runs at a gigahertz or something like that. And of course the computers in front of you are running super fast. But what do you notice about the blue line? Yeah, it didn't keep going straight. It started to go. So for example, your processor now probably runs at about 4 gigahertz. 5 years ago it ran at about 4 gigahertz. Before that, it ran at about 4 gigahertz. Because it got so fast that the amount of heat it generated was too much. They couldn't pull the heat out if you ran any faster. So our processor speed, our single-threaded processor speed has basically leveled off. And it's not getting a lot faster. Maybe it's a little bit here and there, but it's no longer doubling. So what used to happen is, we talked about Moore's Law. There was an engineer named Moore, I don't know the first name, hardware engineer, and what it really was is that the number of transistors on a chip would double every year and a half. What do I say here? Yeah. And so what happens is you double the number of transistors, they all become smaller, you can run them faster. So we doubled the speed. And we went from 4 megahertz to 16 megahertz to 32 megahertz to 64 megahertz, and not necessarily exactly linear, but about every year and a half, the computer became twice as fast. We always talk about how fast is your computer in megahertz or gigahertz, and that is no longer anything anybody asks about, because they're all basically 4 gigahertz. What happened is we couldn't run them faster and faster, and so we started to go in parallel. So the 12 megahertz system I talked about had a single core. And not until quite a bit later in my life did we get to the point of a desktop computer with 2 cores, dual core. And that was an anomaly. In fact, you usually had a motherboard that had 2 processors on it to start with. And then you get a single processor that had 2 individual cores in it. The core is basically a processor unit. You could run 2 things at once at the exact same time. Instruction at a time. And now, of course, what's the maximum number of processors you've heard in a desktop computer? In a desktop computer? Wow. Okay, 192. That's a lot of parallel processors. Right? Because we can't run one processor fast enough, so we give you a whole bunch in parallel. And now that's the way it's going. So the speed that your program can obtain is not based on how fast your processor runs, but how well your program can do things in parallel. If you haven't got your program to run on multiple processors, it runs very slow. But if you've got 192 cores, and you can use all those cores at once, your program runs 192 times as fast. So imagine your frame rate was 10 frames per second, and then all of a sudden you put it across 10 cores, you get 100 frames a second. That's kind of what we're looking at here. So on this graph, I want you to appreciate that the number of transistors is still going up. We're still always getting smaller and smaller transistors, always better performance on that. But the speed of our processors has leveled off. And we end up with a very big gap between the speed and the number of processors. And that's now in parallel. So let's talk about memory and how memory has evolved. So fundamentally, we need to feed the CPU 2 things: instructions and data. Now the instructions, it's usually not that hard to keep up with. A lot of times our instructions are in a loop, and we're doing the same set of instructions a whole bunch of times. We'll have to look at how do we get this data in there fast. But of course, instructions are just data as well. So we need to feed this very hungry processor. This is a photo inside of one of my computers. This big silver thing is actually just a heatsink. It's designed to pull the heat out of the processor. And the processor is sandwiched underneath it, about this thick, sitting there. And here, I've got my memory. In this case, there's only one memory chip here. And it holds all of my RAM, the processor, the information that's running. And it needs to get that data into the computer, into the CPU very quickly. So CPU was getting faster. So memory access had to get faster too. Now, the speed of your memory access is limited by a couple of things. The memory chip speed, and tragically, the speed of light. Because we've got to get data. If my data's sitting in this chip right here, it's got to make it over to there. It's going to be 2 inches. You can only go the speed of light. It's a certain lag in how long it takes to get there. Plus, these chips are not as fast as my processor. So we have this fundamental problem. We would like really, really large memories. We would like really, really fast memories. And what's one other thing you want with your memory? Reliable, sure. But what else? You want big, you want it fast, cheap. I want it big, fast, and cheap. You can't have that. The speed of light says you can't, for example, and a few other things. So that's not going to work well. We want to get there somehow. So memory is, in this case, it's right next to the CPU, but that's far away from a computer point of view, right? When the CPU is actually like, when the processor inside the CPU, the core is maybe this big, having 3 inches or 4 inches away is a long way to go. So Memory is way too slow. Even if you got the fastest RAM on the planet, it's still way too slow. What's the fastest RAM run at? 600 megahertz or something like that. Well, your processor's running at gigahertz, so it's much slower. So what we want to do is we want to solve this speed gap between how fast our processor is running and how fast the memory can supply the data. So first off, we bring in registers. Registers are inside of the CPU. They're part of the actual processor core, and they're accessible inside of a single clock cycle usually, or some variant of that. So you talk about a register file inside the processor, and it can store not a huge amount of data, maybe 200 different values in different forms, something in that order of magnitude. And it's what your processor is using as it's doing its computation. So the register file, it's very fast. It's very close to the CPU, integrated right into the core probably, and it is incredibly fast circuitry. But it's very small. So the next thing we do is we add cache. The idea of caching is that we store a value close to where we need it, so we don't have to get it again. This works on web browsers, you cache it, you have to reload it. It also works on your computer. It turns out that if you used a value recently, you're probably going to want to use that again. So we store it close to the processor. So our cache is much larger than the register. The register holds 200 values, the cache may hold 16,000 values, something like that. It's still smaller than memory though. Your main memory is 5 megahertz or 5 gigs of memory, so it's still a lot smaller than that. It's quite close to the CPU, so it allows fast access time. So we're kind of building a bridge here. We've got really slow, big memory. We've got really fast register file on the side. And in the middle, we put a cache. It's not as fast, but it's not as small either. And nowadays, we actually have processors with multiple caches. We're talking about L1, L2, L3 cache. And the size of the cache and the speed, we can see here that L1 cache is going to be, this is in my case, half a meg, so 500 kilobytes. And then we've got 8 megs of L2 cache, 32 megs of L3 cache. This is kind of the idea. The numbers will change, but basically the idea of we've got the registers, it's tiny, we've got a bigger cache, bigger, pretty big, and then a ginormous main memory over here. We're bridging that gap. If we were to look inside of a core, this is I think a 6-core CPU design. This is sort of a design spec, or maybe it's an X-ray, I'm not sure exactly what it is. But this shows one single processor, one single chip that sits on the motherboard. And inside of it, we've got these 6 cores, each of which can do the same sort of computation. They're usually identical cores. In the middle, we've got our shared L3 cache. Big cache there. And then each of these other cores probably has an L1 or L2 cache in it somehow. And we've got other stuff, memory controllers, I/O parts and circuitry and so forth. Incredibly complicated designs. Multiple cores, we have shared and private caches. A shared cache just means that all of the processors access this single shared cache, for L3 maybe, and then in L1, L2, they might have private caches that only they interact with, that they somehow synchronize with the rest of the system. Yeah, register and caches are on the die. Yeah. We talk about a die being a single chip, the actual physical thing you can drop in step 1. One of the pixels inside, or maybe 20 of the pixels inside of one of the cores, is going to be the register file. Now, I will say also, I'm not a particular expert on integrated circuits here, so take what I say as, this is what the software guy said about hardware. If you happen to be an engineer that's designing one of these chips, don't base your PhD on what I just said. It's at least a good enough explanation to get us through the course. So, we've got this idea of, we've got the tiny thing over here, the big and the big and the big and the big and the huge. This gives us what we call a hierarchy. We want the CPU to feel like it has access to a huge amount of cheap, fast memory. We would like it to feel like, meaning to perform like or operate like, it has access to a huge amount of cheap, fast memory. And we can't. Physically in our universe, we can't pack it tight enough, we can't pack it close enough, and we're not willing to pay the price. We're not willing to pay the price that it costs to make a high-performance L3 cache. We're not willing to make that 16 gigabytes size. That would be unreasonable expense. So what we will do is we will very intelligently move data from each of these maybe 4 or 5 different layers in our memory hierarchy. It takes a long time, from a computer's point of view, to move it from main memory into like L3 cache. And it takes not as much time to move it to L2 and L1. And L1's pretty fast, so we can get that data really quickly. So what we want to do is we want to predict the future. All we need to do is predict what will the computer need next. If we can predict what to put in L1 cache perfectly, it doesn't matter that everything down there is really slow. They're going to be kind of feeding this queue, loading big buckets of data coming in. Are you going to need this in a minute? Here's a big data delivery. And then we'll just kind of refill the L1 cache with just the right stuff. If we could do that, it'd be amazing. We'll see a whole bunch of algorithms that try to do that intelligently. Now, one thing I didn't mention is the hard drive. You got small, bigger, bigger, bigger. We got a huge main memory here, and then the office building to our side over here is your hard drive. But unfortunately, there's a whole bunch of snails that retrieve data. Even if you have a really fast, like SSD, compared to main memory, it's slow. So, particularly spinning hard drives are absolutely nightmare on performance. Anytime you have to read or write data from the hard drive, your performance just died. Doesn't matter how fast the rest of it works. It'd be like trying to have a relay race where you've got the fastest sprinters in the world and a snail in the middle. Doesn't matter how fast your sprinters are, the snail is going to dominate performance. So this is what it might look like. The registers, the cache, main memory, solid-state drive, hard drives. Down here, the tape gets really slow, but really, really huge. If you're talking about data like Amazon, you're storing data in the cloud, they talk about how hot your storage is. You've got hot storage, it means that your data is accessible probably on an SSD, maybe a hard drive. You've got cold storage, or frozen storage. Frozen is it's on a tape, and it's in that room on a wall, and you want access to the data, we'll queue it in the system, we'll be able to give you the data tomorrow, or something like that. So how cold the data is based on how slow it is to get it out. And of course, so access speed, CPU is super fast, tape is very slow because you have to wind the tape to the right spot before you read the data. But size is a trade-off. By working this hierarchy effectively, we can make it look to the computer like we have a very fast, large memory. That's the goal. So our trade-offs. First, cost. A bigger size typically means more expensive. At a particular thing, like an L3 cache, a small L3 cache is cheaper than a big L3 cache. You know this, a small hard drive is cheaper than a big hard drive in the same category. So if you want more memory, it costs you more money. Next, distance and access speed. Distance and access speed. Faster means closer to the CPU. You can't put everything super close to the CPU. Things do have to physically be further away. You cannot put a tape reader on the CPU. You can have the driver, but you cannot actually mount a tape that speeds data through the CPU. And finally, we talk about persistence. Persistence is the idea of when the power goes off, what data is retained. You know this because you've been working on your resume or your essay, and inevitably what happened? The lightning hit the power pole, your whole house went dark, like it's fine. Computer turns back on, you've lost it all. Now, nowadays, in fact, programs will store the data to your hard drive. Hard drive persists data. Main memory is not persistent. So main memory is a temporary storage. So you can think of it as kind of get commit. If you commit the data, it's saved. But if you don't, then it is not persistent. The final thing here, last trade-off to talk about is reliability. So, for example, SSDs are faster, but in one sense they're quite a bit less reliable. They have known wear-out patterns. They will wear out. And so in fact there's a lot of technology on an SSD to prevent it from wearing out. They talk about wear leveling and so forth. So depends on the reliability you need. Tapes are generally very reliable, but even those can go wrong quite easily. So you got to be concerned about the hard drives, SSDs, and tapes' sort of reliability. There's a great report. One of the large data providers online has a report on hard drive reliability. They've got thousands of hard drives running all the time. And they talk about how many drives they got compared to how many died in a particular period of time. But no matter what hard drive you buy, it's going to fail eventually. And so you can find out, okay, how long can these things actually last? So those are the factors we're caring about. Let me pause here. That was the brief introduction to memory. We are going to spend at least a week and a half, maybe two, talking about coming up with a magic algorithm that gets data to move through, up, and closer to us. We'll talk about how we do that. But at the moment, any questions we can answer on the idea of a memory hierarchy? Yeah. Tape would be data tape backup tapes. So it'd be more like a movie reel. So it'd be this big, and it'd be physically loaded from probably have an automated system that would load it off the wall and put it in the drive, and it would spin it. So yeah, it's not like a cassette tape necessarily. Although I did have a computer that would back up to a cassette tape. It never worked. Any other questions? Okay. So let's talk about instruction set architectures. ISA. So in ISA, you know this. We talk about RISC or AMD. So RISC 60 or ARM 64 or AMD 64. These are two different. We talk about instruction set architectures. An instruction set architecture defines a set of instructions the CPU can perform. Defines the set of instructions the CPU can perform. They can all add, well, almost all of them. Famously, it was Pentiums couldn't divide, I think. So one Pentium had a division bug that would sort of screw up a digit in its division, but most of them are really reliable. So they can all add and divide and subtract pretty much. But exactly what that instruction looks like. Does it take in, do you say I want to divide two numbers and you hand it the two numbers? Or do you say I want to just do a divide and it knows where to go looking? There's a lot of different ways that these instructions can be written. That's the difference between different instructions and architectures. So what happens is your compiler is specific to your architecture. If you're running a Mac M whatever, which is the Apple Silicon, it's running ARM. And the compiler you're running is designed for the ARM processor. So when you compile Hello World, it generates instructions for the ARM instruction set architecture. If you're running other processors, it's probably AMD 64. It's got a compiler that generates AMD 64 instructions. And so the actual executable that gets produced is dependent upon what you can run. Which is why for assignments, we will ship two versions of the checker. You've got to run the right one. Because if you're on a Mac, Apple Silicon, you've got to run the ARM version of that. So we've got x86, or now it's called x64 or AMD 64. We've got ARM on 64, RISC-V, or RISC-V is a new one that's kind of gaining adoption. Those are the different categories. For most of those, we talk about how many bits is our architecture. Basically, the idea is every time you do something, how many bits can you do it with? So the original, I think, Nintendo was, 8-bit. And then we had N60, the Super NES, I think it was 16-bit. And then we got to 32-bit, and then we had the N64, which was a 64-bit system, and so forth. So every time it did an operation, how many bits of data could it do at once on that operation? And this is a fundamental kind of design of not just the processor, but it kind of carries through the rest of the system as well. So for example, if my processor is able to handle 64 bits of data at once, my cache needs to support that. And all the different levels of my system have to be sort of set up to work with that. We will care quite a bit about this 32 versus 64-bit, because it determines the register size. If I've got in my processor my register file, I've got a single register that holds some data. On a 32-bit system, that register is probably 32 bits, unless it's special. Modern systems are very often 64 bits, so you can handle more information. It seems kind of whatever. I mean, you count the number of people in the room. I don't care if it's a 32-bit number or a 64-bit number. When does it start to make a big difference about 32 versus 64-bit? Yeah. Yeah, the address size, the memory. So if I've got 32-bit registers, my pointer is 32 bits. It's a lot. But it's not that much. What is, anyone know off the top of the head approximately what is 2 to the 32? 4 gigs. That's why 4 gigs was a hard limit on memory for a long time. Because the actual computer couldn't possibly address memory beyond 4 gigs. If every pointer you've got is 32 bits, you can only talk about 4 billion different places in memory. You can't even talk about the 5th billion place. I can't count that. That's simply not a number we can represent. So we went to 64 gig, or 64-bit. You don't know what 64-bit is approximately? Yeah? 9 quintillion. Yeah, there's something as ridiculously high as that. Yeah, I'll talk about the number actually in the next slide or something. But you've got an unbelievable, you've got 4 billion squared. So you've got 4 billions of memory lined up. That's the maximum size of the address space now. So when we go to 64-bit, we really care because we talk about the memory size. I don't know if we're going to get to the 128. It's no longer quite so interesting to double this again. I'm sure we'll get there. But it's no longer so important from a memory point of view. Okay, let's do a couple of quick recaps on what we know about C programs. We'll do the ABCD thing so you can pull your phone. Which of the following best describes a pointer in your C program? You'll note I didn't put in here the source of all my nightmares. That may have also been accurate, but we're looking for one of these 4 best describes a pointer in a C program. Give me a second to read those. Okay, let's lock in our votes. What do you think? Also in the middle of the ABCD app, there's a question mark. I'll just highlight the fact that the difference between everyone knowing the right answer and everyone not knowing the right answer looks the same. So if you're looking at me like, I don't know, was it so obvious you're about to fall asleep? Or was it so out there you have no idea and are about to fall asleep? So by telling me, even the question mark says, I don't know, I'm awake, but I really don't know yet. I don't care. So what do you think in 3, 2, 1, what do we got? B's, yes. Wow, that's a lot of B's. Yes, the answer is B. A variable storing a memory address is your pointer. The pointer is. Other things in here, we talk about memory addresses, well that is an address, the pointer actually stores it. An array in C is a pointer. A variable is the same sort of thing, but an array is an area of memory. And the address of the current instruction, we talk about the program counter, which is where in memory we're pointing to. Next one, which of the following is true about this code? I've got size of here. I've got 2 variables. I've got a char star and a long star. And I'm comparing the size of p letter compared to p counter. Is the size of p letter less than, greater than, the same as, or it depends on if the system is 32 or 64 bits? I'll give you a second to figure this or to think about this. 5, 4, 3, 2, 1. What do we got? Quite a few C's, some A's, D's, and question marks as well. Cool. So the answer is C. Anyone want to speak to what you're thinking about this? What goes into that? Yeah. Yeah, so they're both memory addresses. They're both pointers. They're both an address. Now, sure, what it points to is different. So, for example, it is a fundamental truth that the White House is bigger than my house. But the address of the White House is probably about the same size as the address of my house. I don't know exactly what the address is of the White House, but the addresses are the same. So the addresses are the same size, and so my pointers will be the same size. If you've got a single byte in memory, or you've got 64 bytes in memory, you still have a pointer pointing to it. The pointers are the same size. So that's why here, the answer is C. Pointers store addresses. All pointers are the same size. Yeah. Yeah, so you read pointers backwards. So if you've got const, stars, and data types, this is a pointer to a long. If I started throwing constant in here as well, it'd be like a constant pointer to a long that's constant. So it's a pointer to a long, which means that when I dereference my pointer, I'm going to have a 64-bit long. Okay, any questions on this so far? Good questions. Okay, so let's talk more about this 32 versus 64-bit, what the implication of that is. In a 32-bit system, you can do 64-bit computations, so it's not like in a N32 old Nintendo, it's not like it couldn't compute larger values. It would just take 2 instructions to do that. So it's like you add one part together, and then you add the next part together, worrying about the carryover. So if you do it, it just took 2 instructions to do, and the way that the data flows through the system is of, in this case, 32 bits at a time. If you want to do a 64-bit operator, you've got 2 values that get added one after the next. So our register size is our pointer variable size. We have to talk about the word size. You know, there's bits, nibbles, bytes, and working up with the shorts and so forth. A word is sort of the fundamental size of the architecture. In this case, the register file, the registers. So a 32-bit system, the word size is 32 bits. A 32-bit system, as we said, can use 32-bit pointers. A 64-bit system uses 64-bit pointers. they seem obvious, the implications are fairly strong. So for example, here, I've got a 64-bit value, I think. This is my address of some pointer I've got, and it's going to point to somewhere in memory, some data that's sitting in my memory. We want to know about the address space size, which is that how much memory can you possibly work with inside of this computer? Anyone know what Bill Gates was famously quoted or misquoted as saying with memory size? Yeah. It's kind of the right idea. You're off by a couple orders of magnitude, though. Yeah, the quote was, 640K ought to be big enough for anybody. Can you imagine having your computer? This computer has 64,000 bytes of memory, which is 0.64 megs. Right? Famously wrong, I don't think he actually said it, but it's sort of the idea that Windows, like DOS 6 and DOS 3.3 are all on. So the pointer size controls your memory address space. How big can memory possibly be? Not physically currently, but just what kind of numbers, what's the biggest number you can possibly imagine in the computer? So based on this 32 versus 64-bit, that controls what we call the bus width. When data is being transmitted from memory to the CPU, how many bits are sent at once? 32 bits or 64 bits in one operation. Memory channel width and so forth all come down to that. So with a 64-bit system, we're going to need 64 wires to transfer the address from the CPU to the memory, and we're going to need 64 wires to transfer the data from memory back to the CPU. That's the bus width. Now it turns out it's a shared bus and a few other things, but we don't really care about those details. Okay, so let's just put this in context. Imagine the government uses the following form to identify a house in your town. This is the form. House number, street number. Each house has a house number, each street has a street number. We're doing base 10 only here, not binary, not base hex, or whatever you like. How many total houses can be in this town, as per the government? All right, in 5, 4, 3, 2, 1. Locking your votes, what do we got? A lot of people still thinking. I'll give you another second. This is the 3-second bonus. You will not get this on the midterm or the final, or the quizzes. 3, 2, 1. Vote is? We got a number of C's, some B's, some D's and A's as well. The answer is going to be C. You can put a 0 through 9 in every one of those. So we've got 10 possibilities in each one. There's 6 different digits. We've got 10 to the 6th. One way to think about it. Another way to think about it is you've got 9. You put a 9 in each place. You get 99999, which looks like it's answer B. But 0. Yes, 0 counted as well. So you get 1, and you get a million possible houses in this city. So if I were to tell you instead of house addresses, I said byte addresses, same thing applies. We're talking base 2, same thing applies. So the size of the address you are allowed dictates the maximum number of things you can have in that address space. So if you have an 8-bit system, your pointers are 8-bit, therefore you can address 256 bytes. That's it, in memory. There is no 257th byte. We simply cannot comprehend that address. It is beyond the scope of the address we can work with. Now, they do some funny things with addresses, so I've worked on 8-bit systems that'll do 4K of memory, but they're doing funny things with it. So the way that we think of memory is byte addressable. Every pointer is the address of a single byte, 8 bits, in memory. And so here I've drawn what memory might look like. You can imagine it starts down here on the left at 0, 0, 0, 0, and goes all the way up to however big we're talking. And in the middle, there's going to be something. Here I happen to put it at F1001234, arbitrarily. This is a single byte in memory. At this byte, I happen to store a 9. This is the way that my memory is. And I have a variable called p letter, which is a pointer to that small. This is a good kind of working model for how this could work. So memory is made up of bytes. Each byte has an address. We talk about byte addressable. Each byte in memory has an address. In here, I've got each of those cells is an individual byte, which therefore has its own individual address. In a 32 versus 64-bit word, or 32 versus 64-bit system, the number of bits is the number of bits stored in the CPU register. 32-bit system has addresses of a 32-bit size. We can go from zeros up to Fs, and 8 Fs here, which is 32 bits all set to 1 versus 32 bits all set to 0. And the data is retrieved from memory, 32 bits at a time, which is 4 bytes, but the memory is still byte addressable. We tend to pull up these at once. And it turns out that when you're talking memory addresses, the memory address is in the middle between 2 words. You really can't access it. The hardware won't allow it. We'll get to that later. So this is just the idea. We've got all this space in memory. We byte address individual things. So we've got the same picture as before, same values. I have here a little bit of code. Imagine the following code had run. I create a character named CH, I set it to be the value A. I create a pointer named P letter, and I set it to be ampersand CH. Which of the following 4 things is going to be true? P letter equals A, P letter equals 0, 0, 0, A, P letter equals F1, 0, 0, or does P letter equals F1, 1, 1. Give me a second to figure that out. Basically, the question is, what sits inside the yellow box on the right? these as well. The answer is, look at this, we check the video, the diagram, and it's address 1, 2, 3, 4, so this is going to be D. Why? Well, we create a character, we set it to the value A. It turns out that that happens to be in that memory location. We can't necessarily tell that from all the things going on, but we can see kind of from here, the diagram tells us. So then what happens? Well, we set P letter to be a pointer. So that's that char star here on the left. Incidentally, it doesn't matter if I put the star here on the char side or the P letter side. It doesn't matter. C doesn't count. So I create my pointer, and I set it to be ampersand CH. What does the ampersand mean in C? Yeah, address up. It takes the address of the variable. So the address of the variable CH, which happened to be F1000124, and we set that to be the address stored in P letter. So that makes the answer D. Now that's almost true. Anyone here got a very keen eye and is pedantic? When I run this code, what actually happens? Oh, could it possibly point to the memory before the actual place? No, it's going to point to here. That's where it got stored. It turns out if we stored another character right after this, it would actually skip 3 bytes in memory, move on to the next one. Everything is word aligned, a few other kind of funny things. So the way things happen with the compiler and the hardware, we're not going to care too much about that, about where things actually kind of end up specifically, other than we're going to kind of manage the requirements there. So it is actually going to be 1, 2, 3, 4. I missed a semicolon. So, oops. Next one here. Which of the following is true? This is kind of a bit of background knowledge. I haven't mentioned it any time today. This, of course, is playing it kind of fast and loose. Which of these is basically true? 5, 4, 3, 2, 1. What do we got? The answer is, you got B, C's mainly. The answer is C. 1,000 is a kilobyte, so 1,000 bytes is a kilobyte. A million is a meg, and a billion is a gig. Sort of. Why sort of? Yeah. So, you're talking kilobytes or kibibytes, and they're slightly different. Anyway, so sometimes in computing, very often in computing, we don't talk about 1,000, we talk about 1024. Because 1024 is 2 to the 10. Nicely, 2 to the 20 is a meg. 2 to the 30 is a gig. 2 to the 40 is a tera, and so forth. So this is sort of playing a little bit fast and loose. I do expect you to know the difference between KM and G, for kilo, mega, and giga, for example. So a byte is less than a kilobyte, less than a megabyte, less than a gigabyte, less than a terabyte, and from then on, we don't really care anymore. If memory, so if RAM, memory, stored just 16 bytes, i.e. 16 locations, how many bits do we need? What is the minimum address size to address 16 bytes? I'm not going to pull them straight now, but I'm thinking, if you've got 2 bits, you got 2 digits, each digit can contain a 0 or 1, so 2 digits can access how many bytes in memory? 4. 4 bits can access how many bytes in memory? 16, that's the one we're looking for. 8 bits can access 256, and 64 bits can get you, or 16 bits, pardon me, can get you 64K. 65,000. Incidentally, your powers of 2 should be your superpower by the time you graduate. I was doing an escape room with some friends. We had to convert hex to decimal, I think it was, or something like that. There was some sort of code, and they gave you the decoding key that kind of gave you hex on the wall. And so my friends were like, okay, so we got an A, and that's going to be what in binary? I think it was binary to hex or something. And they were going to manually, I'm like, no, step aside, I got this. It's 10111011110. Like, so that's my superpowers. You can pick your own superpower. Say sorry? Yeah, it was in Pandora's Locks in the US. They might have replaced that one. So we are going to take a break in a minute. I want to finish this first section of talking about the hardware, and then we'll take a break, and then talk about the OS. So why are computers 64 bits? Now, well, the big thing we talked about already was memory size. The registers are 64 bits, the pointers are 64 bits. This allows us to address 2 to the 64 different bytes in memory. What is 2 to the 64, you asked? Well, there it is. It's like how many digits of pi can you recite? How many digits of 2 to the 64 can you recite? Fundamentally, you don't need to know. It's just a really, really, really big number. It is 4 billion, 4 billions. That ought to hold us for a while at least. So it turns out to be basically 16 exabytes, if you want to give it a name. It's huge. So that is a lot of space. It's going to be enough for the foreseeable future. So in a 32-bit architecture, how much memory can the CPU access? I'll just give it to you here. That's going to be this one here. I don't expect you to memorize it. Knowing it's 66 or 4 gigs rather is kind of useful, but it's just basically not. What is 2 to the 64, or 2 to the 32 rather, gives you 4 billion. Okay, so let's take a 5-minute break here, so we'll come back when that clock reads 3:30. Let's go 3:40, to give us a 7-minute break. At 3:40, we'll start up again. We'll talk about the kernel and then applications. If you have any questions, come talk to me in the break. Okay, everyone, let's resume the show here. Make sure I got the mic on. My usual trick, incidentally, is after a break, I forget to turn the mic on. So if you cannot hear me very well after the break, and everyone else has stopped talking, So if everyone stopped talking and you can't hear me, remind me to turn the mic back on. The people on the recording would also love that too. So we've talked about hardware, enough that we care about for this course. We're going to move up the stack here. We're going to talk about the kernel. So what is your operating system? The operating system called OS is, clicking the right spot, there we go, the central software managing the computer's resources. The central software managing the computer's resources. You don't need an OS. You know what a system is called with an OS? Called bare metal. If you're not running on an OS, you're talking about bare metal programming. You do that sometimes, for example, this may or may not be running an OS. That's fine. Doesn't really matter. But for us, everything we do runs through the OS. So our operating system includes a number of things. The main thing we care about at the moment is the kernel of the OS. The kernel is the main part that actively manages the resources. It's the critical core section that does the hard work of switching between processes when you switch times, or managing access to low-level things. The kernel does the low-level resource control. Along with your operating system kernel probably came everything else that you actually use. So the difference between Debian and Red Hat Linux is all the second part, the support tools. Everything else built around that, such as the graphical user interface, or the GUI, the command line tools, different things that differentiate what tools. Did they ship Chrome or Firefox with it? Does it include this, that, or the other way of managing this, the file system structure? All of that is generally based on these, or not the structure, but the tools, the file system management tools, are all part of the surrounding things that come with your operating system. So we often talk about like distributions, or a distro, a Linux distro. The difference between different Linux distros is all these support tools. They all pretty much run the same basic set of kernels. They're tweaked in different ways, but it's fundamentally the same kernel. So what does this kernel do for us? I said it manages resources. What goes into that? So resource management, so many programs want access to the hardware at the same time. They're both trying to read in from the keyboard or play sound. The kernel is what mediates this access request. So it manages those sorts of resources. The kernel does program control. Or perhaps the CPU is another resource to manage. The kernel does program control. It will control which programs are running, or stop, or getting loaded. And which of the programs, I've got maybe 4 cores, or 6 cores was the diagram we had. Maybe I've got 12 programs that all want to do something. Which programs are allowed to run on which cores? Which has high priority, low priority, how much have they done so far? That's all controlled by the operating system. Next, we talk about protection. The kernel provides protection, or isolation. It provides isolation for users and programs. So, if you were to log into linux.cecil.sfu.ca or something, that one computer, we could all log into that same computer. But unless we're explicitly sharing information, there should be no way for you to interfere with what I'm doing. I might be fighting for resources, but your program, if your program crashes, it shouldn't in any way affect my programs or what I'm accessing. So our programs are individually isolated, and users are isolated as well. By programs being isolated, when Firefox crashes, Word should not also crash. If it does, you probably have a hardware problem, or a driver problem, or an OS problem. One program should not be able to take down another. So users cannot access each other's data. Programs cannot interfere with each other. And that's a core feature of this protection. Of course, when someone finds a bug in it, it's an exploit or vulnerability. And then you can make it so if I did have a way for my program to affect your program, Amazon cares deeply. Why? Why would Amazon care deeply if I figured out a way with Linux to have my program somehow maybe get data out of your program? Yeah. Yes, Amazon Cloud. So if my program, my hack, is running on the same server, virtual PC, or actual PC, actual system as yours, maybe yours running processing credit card transactions, if I can start to get data out of yours, that's a huge vulnerability. So a lot of work is put into this protection. We think, oh yeah, sure, just my program doesn't touch your program. This is the fundamental thing that makes modern computing work. This is protection and isolation. All right, so how does my OS work? What does it know how to do these things, when to do it? It comes down to usually being event-driven, meaning that your OS doesn't really have an agenda. The OS is sitting there waiting for people to ask for things. This is how our program comes and says, hey, I want some access to the CPU. All right, sure, run the CPU. Another program comes, I want access to the CPU. Okay, you run that one, process it. Okay, and then it sets a timer. And when the timer goes up, bing, kernel wakes up, goes, okay, your time's up, you're off of here, next one goes on, that kind of thing. So the OS is in the middle, responding to events. It is event-driven. The kernel is event-driven. It is responding to these events. There's a lot of different events that can be there. Timer events, software requests, hardware events, like somebody unplugged a mouse. Hard drive is detecting a failure. Those things are events as well. So events here, hardware interrupts, like a mouse click or a network packet. They come into the computer in different ways, but it generates an event to the kernel. We can talk about syscalls. The syscall, we talk about that syscall interface, which is the bridge between your application and the kernel. Anytime an application asks the kernel to do something, that's an event coming into the kernel. So for example, if you want to call printf, you want to print something to the screen, you can't control the screen. You ask the kernel to put something on the screen for you. So we set that in with a syscall for printing. Also, signals are what are called software interrupts. We'll talk about an assignment of ours will actually deal with signal. I think it's assignment 8A. So a software interrupt that announces an event. So for example, segint, which is somebody hit Control C, or everyone's favorite, segv, is a segmentation fault, meaning you've got a bad pointer. These are software-driven interrupts. Inside of the kernel, or working with the kernel, we've got sort of the things that are in the kernel versus the things that are not in the kernel. And as our computer is running, we talk about user mode versus kernel mode. The processor, remember, the processor is just doing instructions. Add two numbers together, write it to here, read it from here. That's the kind of thing the processor does. And if the kernel runs on the processor, and Firefox runs on the processor, why can't Firefox do everything the kernel did? When we talk about user mode versus kernel mode, that's the answer. So the privileged mode of execution is that your kernel runs, it starts up, it's the first thing that runs, it runs in this privileged mode, and then any time it lets anything else run, it turns off privileged mode. It says, okay, I've done my bit, I've done my work, I'm going to let Firefox run on this processor now. There's no special processor for a kernel. It's just running on all the other processors as well. It says, okay, I've been running on this processor now, I'm going to let Firefox take over. And so the thing it does is it reloads Firefox into the memory, it turns off protection mode, and then it transfers control back to Firefox to run. And Firefox does its work and says, hey, I want to print to the screen, traps to the kernel. In that trap, it re-enables protected mode and can work on that. So it's always managing this user mode versus kernel mode switch. We often talk about ring zero. Ring zero is one way of talking about this kind of protected mode. We're not worrying about the internals of the processor, or the kernel, so we're not going to talk too much about this, other than to know that the kernel is allowed to do everything. The user-level program is not. It has to go through the kernel to do it, to make it work. So user mode applications cannot execute privileged instructions. So when the kernel is running, it can access any instruction in parts of the kernel. It'll say, okay, just anything the CPU is capable of doing, it can access. When the CPU says, okay, when the kernel says, okay, we're leaving protected mode, going back to Firefox running, it turns off in the process, okay, we're no longer in protected mode. And now this set of operations is no longer permitted. Anyone who tries to do it is going to generate an exception and crash the program. And, critically, there's no way Firefox can turn on the protected mode flag. Right? That is a protected system. Yes? Yes, the privileged instructions would be part of the instruction set architecture. And so it would define what you can and cannot do, and kind of lock it down so that only the kernel can access the hardware. So modern CPUs will be, each core will be running in one of these two modes, effectively, at any given moment. And in fact, where the operating system is running, there's a lot of different structures to an OS about how it actually comes together. But this gives us enough of a mental model to understand why our programs cannot access the hardware directly, and how the kernel is going to get in the way of that and can make it happen. Okay, so which of the following best explains why we need a user mode? Which of the following best explains why we need a user mode in this user mode and kernel mode setting? Isolation, efficiency, no pointers, abstraction. 3, 2, 1, what do we think? Quite a few A's and some D's. I think the answer is probably best to be A, for isolation. If a program is running in user mode, it cannot access hardware, and it cannot access memory it doesn't have permission to access. It's locked inside of a bubble. I like to think of it as a room. Firefox is running inside of a room, a little universe, and nothing Firefox does can affect other rooms, other programs running in other rooms. We've got this kind of trapped in here. All of its pointers are pointing in this room are still in the room. It cannot escape this room. We'll talk about how that happens, how we work with memory to do that. But fundamentally, having user mode grants us this isolation, so that when Firefox goes down, your game does not go down as well. And when your Firefox goes down, my game on my same computer that I'm running yours on is not affected. I do want to mention the root user. We talked about, if I think about a picture, I think about the kernel is down here in kernel mode, I think about user mode is up here, and then someone asks about the root user. It has nothing to do with this picture. The kernel operates in kernel mode. All of our programs run in user mode. The root user is just, we talk about a privileged user, but it has nothing to do with this privileged mode. A root user is simply somebody who the Linux programs will allow to do anything that they support you doing. Changing files, installing things, that kind of thing. It's set up to check for that. It has nothing to do with this user mode, kernel mode difference. So for example, there's a program called sudo. What does sudo do? Makes you a sandwich. Sudo allows you to do something as the super user. So super user do. You're in a terminal, you try to install Firefox maybe. So you say apt install Firefox. So you can't do that. You don't have permission. So then you say sudo apt install Firefox. And it says, okay, as the super user, which is the root user, I want to do this operation. And then Linux will ask you, what's the password to verify who you are? And if you are allowed to do that, if you are allowed to pretend to be the super user, the root user, it'll then perform the operation for you. Everything I just said happened in the user level. Your program, sudo, is a user level application. The terminal is a user level application. An apt is a user-level application. There's nothing fancy about it. Now, of course, every time I hit a key on a keyboard, that goes to the kernel, but that's just the usual way it happens. So the root user has permission to do a lot of stuff, but it's completely tangential to this hardware idea about kernel mode and user mode. Let me pause here for a second. Any questions? Yeah. Is the kernel the only thing running kernel mode? At startup, no, not necessarily. As the computer starts, there can be other programs that are running to get you there, but fundamentally, once the kernel takes over, that's all that's ever going to run in kernel mode. Part of the kernel, you can put your own code into the kernel with all those drivers. So you can write a driver that runs in kernel mode, but it still has to get in there, and it's still part of the kernel. Any other questions? Yes? When it's in kernel mode, what does that look like to us as a user? You never know. Fundamentally, you've got all these cores in your computer, and maybe you're running one program that's, say, computing prime numbers and printing them to the screen. So as it's computing a prime number, your program is running in a tight loop, doing divisions, that's fine. Every time it prints to the screen, it runs printf, which eventually traps to the kernel. And so your program is basically paused, frozen in time, stuck in memory. The kernel says, oh, hey, it's my turn to do something. You've asked me to print to the screen. You have permissions, where you're wanting, give me the data, let me check the data. Okay, I'll put that over to here, we'll copy it to the screen, I'll pass it to the right driver, and then we're done our work, good, clean up, and return to you. And you're just like, back to life. It was like you're kind of cryogenically frozen while it did its work. You can ask Linux how long something was running in user mode or kernel mode, basically how much work did the kernel do for me. You can use the time command. So you can say time space hello world. It'll tell you how long was spent running user mode versus kernel mode, but fundamentally we don't really know. We don't really care. Good question. Yeah. So again, sorry? If you have a... Yeah, so what is segfault? Every time your program asks for new memory, the operating system basically has access to a big pool of memory, and it says, okay, I'm going to let you access this. And we'll talk exactly kind of how that happens, but you can imagine being in a room here, I can have pointers anywhere, but most of the places there's no actual memory there. Like, for example, this whole wall, there's no real memory behind it. The real memory is maybe just over here. And so my pointers here work just fine. I can do this as my arrays. I can go out of bounds on my arrays, and I can screw up my own data. As soon as I try to access a pointer that would have been on this wall, the OS says, wait, there's nothing there. And so the hardware traps to the kernel saying, like, you've accessed a segment of memory that you don't have access to, or that just doesn't exist in your memory space. So we'll see how that works later. Good question. Yes? Right, so how did anti-cheat software work? They're drivers that install at the kernel level. So that means that anything that's going on, they have full access across the system. There's nothing they cannot see, nothing they cannot do. This means when you log into your bank account, there's nothing they cannot see, there's nothing they cannot do. So a friend of mine, for example, will not install any programs that have anti-cheat software on his development machine. He runs his own development business because he cannot let them have access to his code. Now, do you trust them? I don't think Steam is trying to get my bank account information, but that is something that is possible if they got a bug in their software, somebody can hack that in, and they get access to it. Yeah, and it's adding something in there that is basically trying to make it so that nothing running in user level can be unseen. Perfect visibility user level. So, just put your hack into the kernel level. And then you've got two things at the kernel level that maybe they can see each other. So it's this chicken and egg game, cat and mouse game. Okay. So fundamentally, the root user cannot access kernel memory or protected instructions. You cannot say, sudo run my program so that I can access the world. That's not possible. What does the kernel look like? So this semester we're going to talk about every line on Notepad. This is a basic architectural map of what the kernel looks like in Linux. Thankfully, it is not just one big mess. You'll note that there's color bands vertically here. There's different subsections. So there's, for example, a human interfaces subsection. Now this is, when they talk about human interfaces, they're using that in kind of a wider sense, like USB and so forth. It might fit under human interfaces. Processing is talking about processes and threads and synchronization between programs. We've got a memory management subsection. We'll talk about these in a second here. But they basically architected the kernel into these subsections so that if you're a kernel developer, you don't need to know everything. I tell my students that abstraction is the gift you give yourself because you don't need to know everything. So if you're working inside the memories over here, you don't need to know about the human interfaces. You've got well-defined interfaces that will allow us to communicate between parts. So I want to kind of walk through a few of the terms. I've just got the top of this diagram here. We don't care about the rest. Just showing us the different subsystems. And we're going to talk briefly about a couple of them. First, about the subsystem. This is our device drivers. The system subsection handles a lot of our device drivers. Every device needs a device driver to control it. So, for example, my clicker here connects via USB. There's a driver in Windows, because I'm running Windows here, that is handling the interaction. My hard drive, my sound card, every one of those has a driver that tells Linux or Windows how to operate that piece of hardware. So my network card has a driver to talk to the hardware and allow it to send and receive data from the physical network. The processing system works with our processes, meaning like Firefox, and threads. If you've got a multi-threaded application, we'll talk about what that means exactly coming up. It handles synchronization between them. So if you want to send data between processes, it handles that, as well as scheduling. We'll talk a lot about scheduling later, about when there's multiple things to be done, which program gets to do it. There's a lot of competing goals with that. And there's a memory system. So it handles, we talk about virtual memory and physical memory, and part of that becomes paging. Physical memory is like that physical thing you just slot it into your computer. I've got 64 gigs of RAM or something. That's your physical memory. The virtual memory is Firefox being trapped in a room like this and able to kind of have pointers that point to things, but it's not the physical memory that it's accessing. And that's done through a mechanism called paging. The last couple, I want to talk about storage. We talk about the file system and the virtual file system. And that's when you go to the terminal and you type ls, you're looking at the file system. You type cd/, it takes you to a different part of the file system, tree structure. So we can look at that. And then finally, there is the VFS. Is an interface, or probably the virtual file system. A virtual file system is an interface. It's some data structures and operations that a file system should support. This is kind of an interesting idea that Linux has, and I think most systems now have. A virtual file system is an interface. It is some data structures and the operations that a file system should support. So for example, a USB memory stick. It supports read and write, for example. You can open a folder, you can open a file, you can close a file, you can read from a file, write to a file. Those are file operations. So it turns out Linux takes this idea and says, well, why don't we apply that to Brian's clicker? So my driver for the clicker I've got turns out to be a file. It looks like a file in the file system. You can open it, you can read and write from it. It's a really clever way of accessing things. So, for example, I'm going to go here to, have I got one ready? I'm inside my environment here. I can go to the proc folder. This is a virtual file system. These are not real files. Well, they look like real files. They're not real files. So for example, if I do cat CPU info, it tells me a bunch of information on my processor. I can copy this file. I can't edit it, it's read-only. But it's not saved anywhere. Every time I access the CPU info, what it does is the kernel gets the call that says, hey, somebody wants the CPU info, and the kernel goes, oh, right, okay, let me go generate that. It goes, okay, I got this many processors, first processor looks like this, and it spits out this information, next processor. So this file is dynamically generated by the kernel. It's pretty cool. Other things that I can look at information about different processes that are running. So under sys file system. Oh yeah, that's these numbers here. So these numbers on the left-hand side, those are the different processes that are running. So for example, I just ran a process called, let's see what it's actually called. There we go. There we go. So these are the things that Linux is currently running. The process ID is 166, 129, and PS itself was 451. You'll notice I got a 1, a 129 here, and there's 66 as well. So I can actually get information on a single process. Let's go and look at that, CR1. This is information on the process that had the ID of 1, which is my shell. My ZSH, process ID 1. Here's a bunch of information that I can access through the console on this. So I can find out, for example, sched. I think it's always scheduling, cat sched. Here's some information on scheduling for this process. So I can find out how long it had to wait, what it's done, how much time it's used, and so forth. This is the virtual file system. These aren't real files in the sense of it's stored on disk, but to all my programs, it looks like a file because I can read and write it just like a file. So that's kind of a cool idea. Yeah, what is a directory? This is sort of like a question, what is life? So the directory is just a way of storing things in different places in sort of a tree structure, which is, the directories generally, we would say, the ones that are actually on disk, they're written to disk, so they're kind of real in that sense. But things like the proc folder is a virtual file system folder. And so we can find that out on computer here, we can run the mount command. And this tells us all of the funny things that have gone on with our directory structure. So it's not just like, hey, I loaded the hard drive and here it is. Kind of like you might think on Windows, like the C drive. But that's not even that, because then there's a user folder and a bunch of other stuff that goes into that. So there's a lot of complexities that happen here with the funny stuff that's happening. So for example, the proc file system is mentioned here a lot because it's a virtual file system that's dynamically superimposed. Is there another question over here? I got the real stuff with the not. In here, if I do ls minus LA, the first character here is the dashes. That means they're not real. If I go to a real place, nope, never mind. Yeah, directory versus not. I can't remember off the top of my head, but basically you can get it so that there's another command to give to ls, and it will tell you if it's a virtual file or not, I think. And it can tell you a few of the properties. So, or no, pardon me, I think I'm thinking about links. I'm not entirely sure with ls how you do that. You might need to check from mount. Okay, let's run on the side. And then also the final one here, we mentioned networking. The networking subsystem, of course, handles network access. So things like sockets, TCP, UDP, and IP. We will talk about this in depth later on as well. So we'll write one of the later assignments will be for doing server and client networking. So we're not going to go into the details of each of these sections. We're going to use a number of the sections. For things like the memory section, we're going to talk about how it works. We're not going to look at the kernel's code, but we'll talk about the algorithms and the structure of how it works. And the reason this is important is when your program does the wrong thing, you know what happened. Or when your program's running slowly, you can identify, like, well, I know what's going on here. I can maybe improve that. So this is not necessarily going to be the kind of thing that you make $1 million off of, but it's going to be the kind of thing that helps you understand what the computer is really doing. So this course might not get you a co-op job, but it'll help you understand all the things that happen on co-op. Okay, so for the kernel, here's the end of my kernel section. Which of the following is true? The root user runs programs in the kernel mode. Syscalls allow the kernel to execute user-level applications. A hardware interrupt is generated when dereferencing a null pointer. The user mode prevents applications from executing privileged instructions. Give me a second to think about that. If you're not sure, please vote question mark. That way I know you're awake and you care. If you don't care, don't vote. In 3, 2, 1, what do we got? Quite a few D's into B's going up. So the answer is D. User mode prevents applications from executing privileged instructions. That gives us that isolation we're looking for. Looking at the other ones we've got here, A for the root runs programs in kernel mode. We said that that's not true, that the root user is completely separate from kernel mode and user mode. Check out syscalls. Well, syscalls do work about application and kernel. The opposition, it's the other way around. Syscalls allow user-level applications to request kernel operations, not the other way around. And then C, hardware interrupt is generated. It is not generated from dereferencing a null pointer. One of the slides I think mentioned that dereferencing a null pointer generates a software interrupt, not a hardware interrupt. Hardware interrupt are things coming from the outside world. Things like a button press would be hardware interrupt. Okay, so the last one to do is applications. It's actually the shortest one we've got because it's just talking about the kind of things we already know a bit about, and then we're going to delve deeper into later sections next day. So briefly, here's Wally pondering, where do applications come from? Well, glad you asked, Wally. First off, we've got the source code. You type in your source code, and then unless you're using an interpreted language, you chose to use a compiled language, so C, for example, we compile it to an executable. We talk about that being machine language or machine code. Your machine code then sits on disk. Eventually, your machine code gets loaded into memory, and only at that point, when the kernel starts and has loaded it into memory and is executing it, does it become a program. So we went through the steps of source code to executable to a running program. When we talk about a program, we mean a kind of an executable that's in motion or an executable that's being run. That's right, a process is an executable being run. So compilation versus interpolation. C, C++ are compiled into machine language. You get that executable file. If it's interpreted like Python or JavaScript, then it runs through an interpreter, and the interpreter on the fly decides what to do. It's a big difference between those two language formats and families. The big trade-off is, of course, portability versus performance. If you've got C, it compiles straight down to the assembly language, or the machine language. It's very fast. But once compiled, you can't run it anywhere else, really. It's got to be on that instruction set, and you're locked to it. Something like Python, however, you can write the code and run it anywhere, but it has to go through the interpreter, which is a bit slower. So the compilation is not portable. When you compile the code, you get one specific instruction set architecture support, and you're stuck with that. So AMD or ARM64, for example. There's a lot that they put effort into making interpolation faster. They talk about just-in-time compilation, which maybe Python, I think, would do. Basically, as it interprets it, it makes it into a machine language so it runs very quickly. But fundamentally, it's offers slower. We will talk about what's called POSIX, which is the Portable Operating System Interface. Portable Operating System Interface, the POSIX standard we talk about. And it defines a number of user-level things, like how to access the operating system and so forth. And it's widely supported across a number of different platforms, Linux being the big one we care about, but it's also supported elsewhere. And so we're going to learn a lot of POSIX stuff. At the top of most of our C files, we're going to need to say that we're interested in a particular version of POSIX. So we're going to say hash define POSIX C source, in this case it's 2008-09, which is probably September 2008. And the L simply says it's a long value. So a lot of our C code is going to have this at the top of it, basically telling our compiler, hey, give me access to the good stuff, where good stuff happens to be 17 years old. You know, the new things. They put this in so that every time they add something new, they put it under a certain, like one of these locks, so they don't break existing code. If they add in something new, it doesn't break existing code. So almost most every one of our files is going to have this hash define at the top. An ABI is another one of these TLAs. Do you know what a TLA is? Yeah, it's a 3-letter acronym. We've got all of them, right? ABIs, and so on. Here, an ABI is an application binary interface. The application binary interface. It sits on top of the instruction set architecture. The ISA instruction set architecture defines what the actual hardware, the silicon, supports. The application binary interface kind of sits on top of that and says, well, when I'm running in this environment, how am I going to pass data around? When I call a function, how do I pass it an argument? Okay, you put it in the brackets. No, at the machine level. When I want to pass data into your function, where does it go? That's coming to the ABI. So it's a little bit similar to an API, which is an application program interface. Talk a little bit about those later on. And an API is at a kind of code level. An ABI, an application binary interface, is all about the next lower level down, about how does data get sent from one function or one module to another at a very low level. So compilers will generate our executables that follow the ABI for a particular OS. So for example, Windows ABI is different than Linux's ABI. So you can't just copy a Windows binary and run it under Linux and expect it to work. It'd be nice if it did. Very nice. Okay, so I think I'll stop here for virtualization. A reminder, if anyone wants to play games during lecture, please make sure you're in the very back row. That way nobody else gets to play it too. There's this effect, if somebody in the front's playing a game that's interesting, there's this cone of people who learn less behind them. So make sure that cone is just the wall behind you. Thank you very much, everybody. I'll see you on Wednesday.
Wow, wow.